To decide that a transaction is unusual, the engine has to know what usual looks like for that card, its average spend, how many times it has been used in the last hour, which cities it normally appears in. That is memory. And the obvious place to put memory is a database, which is exactly what we spent episode 1 proving we cannot afford. So where does the state actually live? In this episode, keyed state, in Flink, running aggregates that update as each event arrives, and the thing that catches almost everyone out the first time, which is what happens when events turn up late or in the wrong order. Here's the idea that makes it work. When we keyed the stream by card ID back in episode 2, we weren't only choosing which partition an event lands on, we were choosing what state that event can see. Flink gives every distinct key its own private state, and a function running on a keyed stream can only touch the state belonging to the key it is processing right now. One card's running totals are simply not reachable while you're handling a different card. So there's no locking, no contention, no shared table to fight over. The state sits in memory on the task manager that owns that key, behind a state backend that can spill to disk and checkpoint to durable storage. You get the memory of a database without the round trip. In code, it is almost boring, which is the point. We extend a keyed process function. We declare a piece of value state, and Flink scopes it per card for us. So there's exactly one profile per card ID, and we never write that partitioning logic ourselves. Then for every transaction we read this card's memory, update the running aggregate, and write it back. Read, update, write. No query, no connection pool, no cache to invalidate. The important line is the last one, profile.update. That is the whole persistence layer, and it is happening in memory in the same process that is evaluating the rule. Now the part that trips people up. Every window and every aggregate has to answer a question. What does time mean here? Processing time is when Flink happened to see the event. It is simple and it is fast, and it is wrong the moment anything is delayed, because a network hiccup silently changes your answer. Event time is when the transaction actually happened, carried inside the event as that millisecond timestamp we designed in episode 2. Fraud rules have to use event time. When we say a 2-minute window, we mean 2 minutes of the cardholder's life, not 2 minutes of your network's mood. Get this wrong, and your rules quietly become untestable, because the same events replayed give you a different result. Choosing event time creates a new problem, though. If a window covers 2 minutes of event time, when do you decide those 2 minutes are over? A terminal on a bad connection might deliver its transaction 30 seconds after it happened. That is what watermarks are for. A watermark is the stream saying, I do not expect anything older than this anymore, so go ahead and fire. You set how much lateness you will tolerate, and that number is a direct trade between latency and completeness. Allow more and you catch stragglers, but decide later. Allow less and you decide sooner on incomplete evidence. And for whatever still misses the cut, send it to a side output rather than dropping it. Because in fraud, an event you silently discarded is the one you will be asked about. So we have a stream, windows over it, and per card memory that survives failure. What we do not have yet is a way to express an actual fraud pattern, something like a small test charge followed by a large one within 60 seconds. Next episode, the rules engine, and how to write patterns as code an analyst could read. See you there.